Hello everyone. In this set of video lectures, I'm planning to cover few aspects and the importance of modal analysis. I'll be covering this topic basically in two parts, and then subsequently we'll see some examples of modal analysis or how to perform modal analysis using ANSYS Workbench. So, before actually going to the formal definition of modal analysis, let us just discuss about this classic example of Tacoma narrow bridge. This bridge was a comparatively a very long bridge. In fact, that time it was one of the third longest bridge which was built with the longest span of around 0.8 kilometers and with the width of around 11.88 meters. Now, girders of as deep as 2.43 meters were provided for this bridge in order to provide some stiffening to it. But the thing was, although the construction had started in 1938, it was open for traffic on this date, that is 1st of April 1940, and just after 4 months of opening this bridge, it collapsed very badly on 7th of November 1940. So within just 4 months, this bridge collapsed. This is the opening day of this bridge. Okay, and the reason for this bridge was not corruption and all as such, or not because of the static loading, but the reason for the collapse of this bridge was because of dynamic loading. Okay, this if you just look at this bridge here, normal ups and down kind of vibrations were observed throughout its useful life. Even we experience this kind of ups and downs even nowadays on some bridges, right? But let me remind you again, almost 8 feet tall steel girders were used to stiffen this bridge. All right, and throughout its useful life, these ups and down movement were observed. But what happened on the 7th November 1940, that is at around 10 a.m., was it started experiencing a steady wind of around 64 kilometers per hour, and this led to something called as the resonance of this bridge. Okay, now this word resonance we will see in a while what this word resonance means. And then it started experiencing a torsional mode. All right, it started experiencing a torsional mode of vibration. You may observe it here that it is experiencing a torsional mode, right? It is getting twisted about its nodal line. Okay, so all these words, resonance, torsional mode of vibration, in fact this, what do you mean by this nodal line, all this we will see in a while, right? So basically it started experiencing a torsional mode because of the wind which it was experiencing. Now that led to oscillations of this bridge in the torsional mode, and then it kept oscillating that way for a while. Okay, in this next clip you will see this professor who is coming back, who is trying to come back from the bridge, who had actually gone there to actually study what is happening in this on this bridge. Okay, the oscillations were very high. The oscillations were in fact a very crazy oscillations that were observed. So this professor actually went to study what is happening over there, and he's trying to come back from this bridge by following this center line. Okay, in fact this center line can be termed as a nodal line in terms of modal analysis. Okay, wherein actually these are the points where there is no movement that is observed in the structure. All right, so he's trying to take the advantage of that, and then he's trying to come back, uh, he's trying to come out from this bridge. And then in this last clip finally you'll be able to observe the collapse of the bridge. Okay, it happened at around 11:10 a.m. So it had started experiencing this torsional mode at around 10 a.m., and within 1 hour this bridge totally collapsed. So basically what led to the collapse of this bridge? Okay, many engineers, many physicists over the next decade, so almost for next 10-15 years, they studied many things with the example of this Tacoma bridge. Okay, and then hopefully at the end of these two parts of this video, even we should be able to understand what actually went wrong. uh, so when we say modal analysis, basically this modal analysis is the first step for the for something called as dynamic analysis. All right, so modal analysis is the first step. This is the first step to perform the dynamic analysis. So basically this modal analysis will give us how the structure behaves on its own. All right, it will give us, it will try to give us some inherent properties of this, of any structure. So that is why the modal analysis is the first step of dynamic analysis. So once you perform this modal analysis, once you understand the inherent dynamic characteristics of any system, with the help of that, then you can perform the remaining analysis like harmonic analysis, or say transient analysis, random vibration analysis, and so on. Right, so modal analysis is actually the first step of performing the dynamic analysis. Okay, I know I have not yet told you all exactly what this modal analysis is, but before even going into that, let us just try to understand, let us just try to revise our concepts of degrees of freedom for a discrete system. All right, now as we know, this is our famous spring mass system. All right, now the degree of freedom of this discrete model, spring mass system model, is 1, right? So this is of 1 degree of freedom spring mass damper system, spring mass system. Okay, there is no damper here, so this is just a spring mass system. Now why we call it as a 1 degree of freedom system? Because at any given time we just require one coordinate, right? From this position we require just one coordinate to basically give the, or to basically define the position of this entire system. We just require one coordinate. So therefore we call this kind of system as 1 degree of freedom system. Now since this is a 1 degree of freedom system, it will have only one natural frequency with which it will oscillate. What do I mean by natural frequency? Suppose if this is the mean position, and at this mean position if I disturb it, if I give it some oscillations, then it will start oscillating about the mean position, right? But that oscillation will be with one particular frequency, and that is called as the natural frequency of the system. It doesn't depend upon the external factors. It is totally the inherent property of this system. So therefore with only with that frequency it will oscillate, and no matter what is the amount of disturbance you are giving this you are giving to this system. All right, from this mean position you may disturb it up to here, or say up to here, but it will oscillate only with its natural frequency, that is omega n. And since this is a 1 degree of freedom system, it will have only one natural frequency. All right, if we take the second example, now this is a pendulum with 2 degrees of freedom system. All right, because there are two discrete masses, and in order to define the position of this system at any given instant, we will require two coordinates. One coordinate to describe the position of this mass, and the second coordinate we will require to define the position of this mass. Okay, so this is basically a 2 degree of freedom system, and since this is a 2 degree of freedom system, it will have two natural frequencies. All right, it will have two natural frequencies, and then we can similarly we can even have a multi degree of freedom system. All right, these are basically, they are called as, if we have 3 or more degrees of freedom systems, then we can call them as multi degree of freedom system discrete, multi degree of freedom discrete systems. Okay, so since this is a multi degree of freedom system, since this is a multi degree of freedom system, it will have n natural frequencies. So it can have omega 1, omega 2, up to omega n. So this, where this n is basically the number of degrees of freedom. Right, in this case it has around 1, here we have first mass, second mass, third mass, fourth, and then we have fifth mass and sixth mass. So it will, ideally speaking, this discrete system should have 6 natural frequencies. And this is very easy to understand about this discrete system. But what about continuous system? Suppose say if we have a continuous system like this. Now this, if you look at this structure here, if you look at this structure, if you look at this entire structure, it is a kind of a, what, this is like a cantilever beam, right? It is like a cantilever beam. Why I'm calling it as a cantilever beam is because it is free at this end, whereas it is fixed at this end, right? This is a kind of a cantilever beam. But now it is a continuous system. In this system now we cannot nicely differentiate between what is the where is mass and where is spring and so on, right? The mass as well as the spring properties or the stiffness properties are distributed continuously on this system. So therefore these are continuous system. Now this continuous system, as I said, I can idealize it as a cantilever beam which is fixed at one end. It is fixed at this end, right? It is fixed at this end and it is free at this end, right? And we can call it as a continuous system. Now since this is a continuous system, all right, so therefore the mass, since the masses will be continuously distributed, so ideally speaking there should be infinite number of natural frequencies for this system. The reason is it is a continuous system, right? So therefore there should be infinite number of frequencies or infinite number of natural frequencies for a continuous system, right? And then how it will behave for each natural frequency, so that can be seen here. Probably for the first natural frequency it will behave like this. For the second natural frequency it will bend like this. For the third natural frequency it may behave like this. I'm not sure for which natural frequency these mode shapes are, but for some particular frequencies it will tend to behave like this. It will oscillate like this. All right, so these are basically called as mode shapes. These are called as mode shapes. And what are mode shapes? Mode shapes are basically the behavior of the continuous system for a particular natural frequency. So for say omega n1, for this particular first natural frequency it might behave somewhat like this. Okay, it might oscillate about its mean position in this fashion, from edge to edge fashion. Okay, for say second natural frequency it may behave, it may oscillate like this. It will go up and down. Okay, since these ends are fixed, these ends are fixed, there won't be any movement here, so we can call this as our nodal point. All right, and as we keep on looking at different natural frequencies, it will be able to see different mode shapes. Okay, the behavior will be different for different frequencies. And then we can continue. We can by with the help of softwares we can extract as many number of natural frequencies and as many number of mode shapes associated with these natural frequencies using this modern day softwares. All right, we'll take one more example. Now in this case we have here a windmill. I have taken this example from ANSYS website, right? So this is a windmill. Again, if you look at its blade, it is a continuous system, right? It is a continuous system. So if somebody wants to see how this windmill will behave for different wind loads, and it doesn't fail like the Tacoma bridge which we had seen for different wind load, then what one will have to do is one will have to perform something called as modal analysis. How to do that? This one blade will be considered, will be idealized again as a cantilever beam. Why? The reason is it is fixed here at this end, right? It is fixed here at this end. At this end it is almost fixed, and at this end it is free. So one can idealize this to be again a cantilever beam, and then better to find or find the natural modes of this cantilever beam. All right, so that can be done. And then finally, after performing the modal analysis using some software, we'll be able to extract its different modes. Like first mode will be a flap wise bending mode. It will start bending along its flaps. Then one may observe the first here. This is the flap wise bending mode. This is the edge wise bending mode. One may also observe the second flap wise bending modes and so on. Okay, so basically the natural, I mean the modal analysis is nothing but it is the process. All right, the modal analysis is the process of determining inherent dynamic characteristics. Now this is very important. Okay, it helps us in determining inherent dynamic characteristics. So this has nothing to do with any external loads. All right, it will help us to extract the natural frequencies or the damping factors or the mode shapes of any given structure, which may further, which we can use it to understand its dynamic behavior. As I had said in my earlier slides also, the modal analysis is the first step to understand the or to analyze the or to perform the dynamic analysis of any given structure. Okay, now again, this is the same thing what I'm trying to tell you all is also a typical common dynamic simulation for many other dynamic simulations, right? I had already shown you this diagram. So modal analysis will be the a basic analysis or the first analysis which is done in order to perform the dynamic analysis of any system. Once you do the modal analysis, once you extract the mode shapes and modal frequencies, with the help of those modal frequencies and mode shapes, we can perform other types of analysis as well, which I will not be covering in this series of videos, but we may try to do this harmonic analysis or say transient dynamic analysis in later of the classes. Okay, uh, so what we can say is that again I'll give you one more example of this symbol, wherein a drummer is hitting this symbol. He is basically exciting this symbol, and then you can see the oscillations here, right, in the symbol, how it is oscillating for a given excitation. Now basically the dynamic vibration behavior is nothing but, as we have discussed, it is the response of a structure under external excitation. Okay, so if somebody wants to understand the dynamic behavior of the structure for external excitation, we have to start again with performing the modal analysis. Okay, and once we do the modal analysis, we will be able to see how it behaves at different frequencies. Okay, so this dynamic vibration behavior is actually a combination of all this, the combination of all these different mode shapes of this structure. Okay, in this case the structure is this symbol, right? We may actually try to carry out this exercise as our first exercise to find the modal frequencies of this symbol. Okay, so now all this whatever I have explained is in terms of words. Let us try to understand this with the help of some equations too. For example, this is our famous equation that we know, right? Mx double dot plus cx dot plus kx equal to f of t. What is this equation? This equation is the equation of motion under some external dynamic force, that is f of t. But in order to perform the modal analysis, or in order to frame the governing equation of modal analysis, we don't require the external dynamic forces, right? Because as I said, for modal analysis, we are just trying to understand the inherent properties of the structure in the absence of the forces. So I don't require this, all right? And then for many problems, we can just neglect this damping factor also in the structures in order to make our calculations less complicated. All right, so if I now neglect this damping factors, and if I now neglect this external forces, by the way, this is nothing but the mass matrix. Okay, this is mass matrix, this is the stiffness matrix of the structure, this is the displacement vector, and this is x double dot is nothing but our acceleration vector. All right, so finally, in the absence of the external force and the damping matrix, our equation of governing equation of modal analysis becomes this. Now this is a very important equation. Basically, whenever we say we are trying to perform the modal analysis of any system, what we mean is we will try to solve this particular equation. We will try to solve this particular equation in order to find the modal analysis, in order to find the different natural frequencies of any structure. But now your question may be, we are trying to find the natural frequencies, right? But here there is no frequency term. Here we have a displacement term, and then we have the acceleration term. So what exactly happens then? How we can find this natural frequencies from this equation, wherein there is basically it is not a function of frequency as such, but it is a function of time. So what do we do? How do we take help of this governing equation to find the natural frequencies of the structure? So this is what exactly we'll be looking now in our next few slides. Say this is now our governing equation of modal analysis. You know now how we have come to this equation, okay? And then what we can do is, in order to find the natural frequencies from this equation, we will have to convert this problem into something called as eigenvalue problems. And how to do that is, we will have to assume a harmonic solution for this particular governing equation, and this is our nothing but this is our harmonic solution for this particular equation. So what it basically it will do is, this equation, which is a function of time, once I substitute this harmonic solution in this equation, and then once I double differentiate this equation, which will be probably what, minus omega square a sine omega t plus phi, right, if I differentiate this twice with respect to time. So we can substitute that here, we can substitute that here, and then finally we will do the rearrangement, and we'll be able to observe that we convert this particular governing equation of modal analysis in terms of as a function of frequency. All right, so that is what we'll see in our next few slides. That is, we have assumed now this harmonic solution, and the double derivative of that harmonic solution turns out to be this, okay? And where, what is this phi? This phi is basically the amplitude, the maximum amplitude of this harmonic function, okay? So once I have these two solution, and then we know that this is our governing equation of modal analysis. Once I now substitute this equation here and this equation here, and then after doing some rearrangements, we'll finally end up getting this equation. We'll finally end up getting this equation. All right. The adjustments are not that difficult. Basically, we'll have this common term as sine omega t here and here. We can just cancel them out. We'll rearrange it, and then finally we'll get this as our equation. Now you see here, what we have done is, we have successfully converted this problem, which was under time domain, into frequency domain. Now this is the this equation is the function of frequency here, right? And this phi will, this omega will basically give us the natural frequencies, whereas this phi will help us to give the mode shapes, or how the structure behaves for a particular natural frequency, okay? So finally, basically, when we say we solve this equation to extract the natural frequencies, basically what it means is, we simplify it to this equation, and then we solve this equation actually to obtain the mode shapes of any structure. All right, so this is basically now the eigenvalue problem. I have put this suffix i's here in order to take care of the continuous system, okay? Because the continuous system will have how many natural frequencies? It will have infinite natural frequency. So for a first, if I is equal to 1, that means we will be able to extract the first natural frequency of this system, and we'll get a corresponding first mode. If I is equal to 2, then we'll be able to extract the second natural frequency of this system and the corresponding mode shape, the second mode shape, all right, and so on. But when we say we want to solve this eigenvalue problem, the trivial solution would be what? The trivial solution would be directly substituting this mode shapes as 0. That is, we can assume that there is no motion. It is this structure is will not behave, or it will not respond at all. So we can, in that case, we can say that phi is 0. But that will become a trivial solution, right? It will become a trivial solution. Why? The reason is, it will not give us any insight into this problem. It will not give us any useful results. So we'll neglect this trivial solution, and what we will try to do is, we'll actually try to see how to obtain the solution of this equation without going into this trivial solution. All right, so therefore what we do is, so this is what I said, we want to find now basically omega and I and phi I. All right, so in that case, if I want to avoid the trivial solution, the only way to proceed is, we should say that the determinant of this, Okay, the determinant of this part should be equal to 0, because phi I equal to 0 will just give us the trivial solution. So therefore we'll avoid that, and then the only way to proceed is the determinant of this part should be equal to 0. All right, and this from here, once we solve this matrix determinant, we'll be able to find this omegas. Okay, we'll be able to find this different omegas, and once we find the different omegas, we'll be able to find the natural frequency. Okay, let me again remind you, this omega is the angular natural frequency, but if you want to find the natural frequency of the system, we just need to divide that omega by 2 pi, right? You all must have come across this, f equal to omega by 2 pi. Okay, and then once you find this omega I, we can substitute it back in this matrix, and we'll be able to find the corresponding mode shape for this particular natural frequency. Suppose if we get omega 1, we'll substitute that omega 1 here in this matrix, and we'll be able to find the corresponding mode shape and so on. Okay, so this is all about the equations and mathematics behind this modal analysis. All right, here I have taken one example from ANSYS website itself. All right, this is a 2 degree of freedom discrete system. What I was talking about was this. We can we can assume here a solution that x is equal to, say, probably phi sine omega t plus theta or something. Then the acceleration will be x double dot will be minus omega square, and then phi sine omega t plus theta. Substitute it here and here, right? And then you will be able to convert this problem from time domain into frequency domain. You can call it now a eigenvalue problem. As we have seen, in order to avoid the trivial solution, we need to say that the determinant of this will be equal to 0. From here, one will be able to obtain the two natural frequencies, omega 1 and omega 2. Okay, why? For this, of course, for these given values. All right, for these given values, we'll get the first natural frequency as this and the second natural frequency as this. And why we are getting these two natural frequencies? Because this is a 2 degree of freedom system. So obviously we'll end up getting two natural frequencies, and with each natural frequencies we have a particular mode shape, so, for this discrete system. And this kind of numerical calculations is very easy for a 1 degree or 2 degree discrete system, but when we go to a actual structures or a real structures, this approach will really not be possible. Why? Because here the size of the mass matrix and stiffness matrix for a real structures like this will be infinite, because there I said it has a infinite degrees of freedom, right? So that is not possible. This mathematical solutions are not possible for the real structures, although we idealize it. But again, this beam will be a continuous beam, and this approach is really not possible for a real structures. So therefore, the only way to proceed for this is not the hand calculations, but by using softwares. For example, for this particular wing, we can idealize it as a cantilever beam, and then we can use any finite element software. We can discretize this geometry to have from and we'll convert it from infinite degrees of freedom to around, say, in this case it was discretized, and it was found that it has now 1256 degrees of freedom. Okay, again, just imagine, even after discretizing this, we have 1256 degrees of freedom. So that means this matrix will be of 1256 by 1256. Here we have this 2 by 2 matrix, right? This is just a 2 by 2 matrix. But for this problem, although we have discretized it, still we will have the size of the matrix as 1256 by 1256, which is really not possible with the hand calculation. So therefore, the only alternative which we have is to use this softwares. Okay, to use this analysis softwares. So by using this softwares, we'll be able to extract different mode shapes at different frequencies. And then you might have one more question which is very important. Now, since I'm saying it will have 1256 degrees of freedom, theoretically what should happen is that we should get how many natural frequencies now? We should be able to extract 1256 natural frequencies, right? It will have first natural frequency, second natural frequency, third natural frequency, up to 1 to 5 6 natural frequencies. But do you really think all these natural frequencies are important? It will not be that important. Okay, all the natural frequencies are not at all important. Then how to decide how many natural frequencies we should extract from a given structure? Now that totally depends upon to what excitation frequency this structure will be subjected to. Suppose say this structure will be subjected to say up to 0 to say 1000 hertz frequency. The excitation frequency can range, suppose say, within this limits from 0 to 1000 hertz. All right. So in that case, whatever modal frequencies lies within this range, we can extract only those many natural frequencies. All right, and we'll be interested to look at only those many mode shapes. Nobody will be interested to look at all the 125 1256 frequencies, natural frequencies and its mode shapes. Okay, so one has to carefully first understand to what range of frequencies this structure will be subjected to, and only within that range one has to extract the natural frequencies and study its mode shape. And then the higher order high frequency modes it has a very limited effect in the dynamic behavior of the structures. Okay, so we need not go for a high frequency modes as such, but this will be critical. First one should try to understand to what exactly range of frequencies this structure will be subjected to, and then within that range one should extract all the modal frequencies, and then accordingly one has to study the mode shapes. All right. And then finally, one more thing, very important thing is mode shape represents the relative deformation of the structures and not absolute value. For example, when you look at this mode shapes, basically it is not the absolute value or it is not the absolute magnitude. Now what it basically shows is what is the distance that this point is traveling with respect to the fixed point. All right. For example, in this case, now this point here is moving three times this point, right? Three times this point. I'm sorry, this point here, this point is moving three times, this mass here is moving three times this mass. All right. So it is not that this is moving by 3 units, right? It is moving three times this mass. And since this is a vector, if I multiply this vector with some constant, say 2, then what will happen is this will move by 6 unit, whereas this will move by 2 unit. But again that ratio will be what? 6 by 2, which will be 3, right? So this mass is again moving 3 times this mass. Okay, and this mass is moving 2 times this mass, and even if I multiply it by 2, this is moving this 4 by 2, which is again 2, right? So what I'm trying to say here is the mode shapes represents just the relative deformation and not the absolute deformation. This is very important. Okay, one may even try to multiply this by say 4. So what will happen is 4 into 3 will be 12, 4 into 2 will be 8, 4 into 1 will be 4 and 0. So basically this third mass is still moving 3 times the first mass and so on. Okay, so please do not be under wrong impression that the modal analysis gives us the absolute value. No, it will just give us the relative deformation of the structure. Okay, so therefore, this last sentence, for a realistic modal analysis, mode shapes can be plotted on different scales. Okay, now this is on the scale of 1:1, but this is on the scale of 2:1. Similarly, I can plot it for a 4:1 and 8:1 and so on. All right, more about this will get clear when we actually do solve some examples using ANSYS. Okay, scale, while still it represents the same mode shape. All right. So here it is representing the same mode shape in this case as well as in this case. Okay, so this is what I wanted to cover in this first part of this video of modal analysis. Most of this content I have taken it from this website of ANSYS, courses.ansys.com. Okay, so you may as well refer this website to understand more about this modal analysis.